Here I'm going to go over a technique for simplifying radical expressions. It involves identifying and simplifying radicals of perfect squares. So let's give a few examples of simplifying the square root of a perfect square. The square root of 4, for example, can be broken down into 2. The square root of 9 is 3. The square root of 16 is 4. And we could even say that something like the square root of x to the 4th is x squared. So we can do it with numbers and variables. Now, even if a number isn't a perfect square itself, it might contain a perfect square as one of its factors. And if it does, then that radical can be simplified. Let's see if that's the case for radical 40. Is there a perfect square inside 40's factorization? Let's find out. We'll make a factor tree for it first. 40 is even, so it'll divide into 2 and 20. 20 is also even, so we'll have 2 and 10. And 10 breaks down into 2 and 5. Now the primes are 2, 2, 2, and 5. And what we're looking for is pairs of primes. If we see a pair of primes, then that means there is a perfect square in 40's factor tree. So the perfect square is going to actually be 4. And that's the only repeated primes. There's no other repeated primes. There's no other pairs of primes. So 4 is going to be the biggest perfect square inside 40. Now we want to break it up into a perfect part and a non-perfect part. We can use the rule that radical a times b can be broken up into radical a times radical b. So we want a perfect part on the left and a non-perfect part on the right. Now you could write it out as just the primes that are paired on the left because they make up the perfect square part, and then those that are unpaired can go on the right. They're the imperfect part. Now we can multiply the factors together to reveal the largest perfect square inside 40. It's 4. And then we can multiply the 2 and the 5 together to get 10. And it's almost completely simplified now. The last step is to do the square root of 4 like we had done above and simplify it to a 2. So we're going to have 2 radical 10 as our final answer. Try the process for yourself on the number radical 480. And in a moment, I'll give my answer. All right, so 480 can break into 48 and 10. 48 could be thought of as a product of 3 and 16. And 10 is made up of 2 and 5. 16 breaks into 4 and 4, and each of those breaks into pairs of 2's. So when it comes to the perfect square part of 480, it's going to be made up of these pairs of 2's. So when we split it up, the perfect part goes on the left, and then the imperfect part on the right. So let's put radical 2 times 2 times 2 times 2 here. And over here we'll leave behind the 3 and another 2 and a 5. That's these here. They weren't paired. So we'll have radical 16. 16 must be the biggest perfect square inside 480. And then over here we'll just have 30. We want to do the square root of 16 because it's a perfect square, and we'll have 4 radical 30 as our final answer. Now we'll try it with complex numbers. As we've seen in the past, there's no real number that when multiplied by itself makes a negative. And for this reason, the square root of a negative number is called imaginary. I stands for the imaginary square root of negative 1. Let's find a way to simplify radical negative 4. We know that there's no real number that when multiplied by itself makes negative 4. But we still can simplify radical negative 4 if we use the imaginary I. So we have to break up radical negative 4 into 2 parts. A real part on the left and the imaginary part on the right. We can simplify the radical 4, and the only thing we can do with radical negative 1 is to replace it with an I. So the final answer will be 2I. Imaginary numbers are part of the complex number set. Complex numbers will be of the form a plus bi, where a is the real part and b is just a constant, but the bi part is imaginary. If we draw a Venn diagram showing the different number sets, I'll draw the number sets on the right here. First we had the naturals. After that, we added 0 to it to make the whole number set. Negatives were added to make the integers. And then decimals and fractions were included as well, and that made the real numbers. But the complex numbers includes not just reals, but imaginary numbers as well. And it has the letter big C. Let's say we're going to simplify radical negative 72. Let's draw a tree diagram for negative 72. This time, I'm going to take out the negative 1. Negative 72 could be thought of as 36 times negative 1 times 2, for example. And 36 breaks into 6 and 6. That's 3 times 2 and 2 times 3. Now, what we have here is a few different things. We have pairs of 2's and pairs of 3's. This represents the perfect square inside 72. So we want to put those on the left. We're going to put the square root of negative 1 in the middle. And then any factor who doesn't have a pair should stay on the right. What we'd like to do now is simplify what we have as much as possible so we can get to the fully simplified answer. So 2 times 2 times 3 times 3 was 36. That's the largest perfect square inside 72. That's why I broke it down that way. Radical negative 1 can be I, and radical 2 can't be simplified. However, in our last step, we can do this square root of 36 to get to our final answer, which is 6i radical 2. Now, what if we have variables involved? What would we do then? We can include variables in our tree as well. And I don't have to include the negative here if I don't want. I can just put the I in later. So let's see, we'll break it up into 32 and then a variable part. So 32 could be 4 times 8, which is 2 times 2, and 8 is a product of 3 2's. This can break up into x to the 5th and y to the 4th. All right, so we're going to have 5 x's here. And 4 y's. All right, let's identify everything that's paired. There are 4 repetitions of 2's, so 2 pairs of 2's. I see that we have 2 pairs of x's and 2 pairs of y's. All right, so what goes in the perfect square part? Well, quite a bit. We could put 16 there, which is the product of the 4 2's. And we can put in x to the 4th and y to the 4th as well. We have a negative under the radical, so we're definitely going to want I in there. And anything that's left should go here on the right. So there's a 2 that wasn't paired and also an x that wasn't paired. So the 2x remains on the right. Now we can do the square root of this. So we're going to get 4 times x squared times y squared times I radical 2x. And that's our final answer. Try the next one for yourself, and in a moment I'll give my answer. All right, to break this down, we can make a tree. Split it up into a number part and a variable part. Here we'll have 15 times 10, 3 and 5, 5 and 2. When it comes to the variables, I'm going to break it into a to the 8th and b to the 7th. I know that a to the 8th is a perfect square. But when it comes to b to the 7th, that's not a perfect square. But it has a perfect square inside it. B to the 6th would be a perfect square. So I'll break it up into b to the 6th times b. So this is paired. And when it comes to a to the 8th, there's going to be definitely paired a's inside there. And for b to the 6th, we'll have pairs as well. We'll have 3 pairs of b's in there. All right, so all of this is going to go into the perfect square part of our breakdown. On the left, we'll put 25, a to the 8th, b to the 6th. We'll put I in the middle for the negative. And on the right, what's left, it looks like, is a 6 times b. Okay, that comes from the 3, the 2, and the remaining b that wasn't paired. All right, now we can take the square root of this, and we'll get 5, a to the 4th, b to the 3rd, times I, times radical 6b. And it seems like it might be done, but there's actually one issue that we have to address, and that is the possibility that b may be a negative number. See, b is a variable that could stand for anything. It could be a positive number or a negative number. So if b were to be a negative number, then what would happen in this line? The b is being raised to the 6th and then square rooted. So if you raise a negative number to an even power, you will actually cancel out the negatives and the result will become positive. Then you're going to take the square root of a positive number, and no matter what, in this line above, the result of raising b to the 6th and then square rooting is never going to come out negative. But look at our next line. If we were to plug a negative into that and do b to the 3rd, where it's a negative times a negative times a negative, the result could come out negative. And that's a problem. That would be an inconsistency in these two lines. And that we can't have. So we're going to have to make a modification to fix it. And it's as simple as putting an absolute value sign around the b to the 3rd. What this will do is it'll make sure that no matter what happens here, when you raise b to the 3rd power, we're going to make the final answer positive. We also see, though, that if b is negative, there would become a negative under the radical here. But that's totally separate from what's happening over here on the left. We just want our final line to be consistent with the previous line. And sometimes that means introducing an absolute value sign, just to take care of the possibility that one of the variables could be negative. And the absolute value takes care of that issue. Now notice that I didn't do it on a to the 4th. So in the previous line, a was being raised to the 8th, which is an even power. So even if a was originally negative, the result of that would not be negative. And then we square root it, and again, it would not become negative no matter what. In our final line, a is being raised to an even power again, so even if a is negative, the result of a to the 4th will not come out negative. So I don't have to put the absolute value around the variable with an even power.